Hi, my name is Simon Davidmann. I'm from a company called Imperas Software. What we're going to be talking about today in this presentation is about how we can do architecture exploration driven by software, focusing on the ARM Cortex M33 and the adding of custom instructions around a security algorithm. So I've been in simulation for most of my career, and somebody a long time ago said nobody designs a chip without simulation. And we've taken that a little bit further in Imperas software and said that nobody should develop embedded software without simulation. Brief introduction about Imperas. Our focus is on simulation and on tools and debuggers, especially around processor models. We build a lot of processor models, and the focus of what we do is about software and getting people's software to run correctly before the hardware is available. It's about embedded software because all electronic products are defined by software. And one of the things we also do is we help people when they're doing SoCs in the architectural exploration to do with the hardware and the software of that. We're over 12 years old, we're self-funded, we're profitable, and we're from a beautiful UK city. We're not from Cambridge, we're from Oxford, another beautiful English city. And the team that we have within Imperas, we have backgrounds in the semiconductor world and in the IP world, like in ARM, like in MIPS, like in Tensilica, but also in the EDA world, Cadence, Synopsys, and a variety of others, where we've been involved in the bringing of the processor IP to market, but also the developing of the tools to be able to turn those things into the SoCs. So we have a lot of breadth of experience from the chip design, the architecture design, through to the software development in there. And the technology we build are commercial simulators. We build tools, simulators, which allow you to build virtual platforms and virtual prototypes. There's more information at imperas.com. And to build these platforms, what we do is we have a library of models and components, and we'll be talking a bit about those in there. So what I'm going to talk about really is three different things in this presentation. And it's all about how to get the best out of hardware, you need to get the hardware optimized to get the software applications running properly. We're going to talk a little bit about architectural analysis in terms of architectures, but also custom instructions, then talk a little bit about software development and analysis, and then talk about how we're driving the users in the market for that. So let's now move on and talk about architectural analysis, the first part of it. So there are many different approaches in getting hardware to be efficient and to run the software the way that you want it. And there's different reasons for going down different routes, depending on what you're trying to target in there. You may have some proprietary algorithms you want to put in silicon to accelerate them and protect them and have them run very fast like that. And they tend to be very fast if you turn them into silicon, but they're very inflexible if you want to make changes and things like that. More and more people turn their sort of hardware algorithms actually into software state machines, actually. But people can, to accelerate software, you can build accelerators. A second approach is you try and split your algorithms and run them on maybe a multi-core design. And it could be several processors, they could be the same type of processors, or they could be heterogeneous, where one is targeted to specific bits of the algorithm. But that really does depend on how the workload, how well the workload can be partitioned to be split. Often single-threaded applications are very hard to work out how to break them up and how to partition across multiple cores. And another approach is to change the architecture, the instructions, and the architecture of the machine. And you may be able to put different pipeline stages in, do things in parallel, and that can be very good for certain problems, but maybe not for specific problems. And often you might have specific algorithms you want to speed up, where you've got a processor that does most of the software well, and a good approach to do that is to use custom instructions and add new instructions for the specific bits of the algorithm. And they can be a very good answer in terms of flexibility and also performance in there. So when we're thinking about algorithms, back in the, early 50s, 60s, IBM was building lots of big computers, lots of engines, and was trying to get them faster and faster. And one of the young engineers, Amdahl, had an idea of making things parallel and ended up splitting his own company off and doing plug compatible IBM stuff. And he came across what's now called Amdahl's law back in the 60s, which was basically saying if you're trying to parallelize things, the real challenge is the points where things get synchronized, the bits that you can't parallelize. They're the problem. And that's what the Amdahl's law is really about. And when people are trying to get algorithms faster, so today we have Moore's law, another computer architecture, basically said that we're going to get more and more silicon available, more and more transistors available. So we're going to be able to build bigger and bigger chips. And people couldn't get the performance in terms of raw speed of those. So they started thinking, well, how can we parallelize things? And that's back to the Amdahl thing a bit. And if you look at this chart, the top is Moore's law saying we're getting more and more transistors, and single thread performance was sort of dropping off with it. And so what people have done, they've added more cores to try and improve the performance of their applications. So there's several different challenges and several different approaches. And today we have lots of different algorithms we want to speed up. And for example, there's a huge opportunity for new architectures to gain performance in the AI and machine learning space. And to just build a processor which has certain bits faster really is not really a good thing to do. It has to be driven. The competition needs to be driven by what software is going to run on it. And you can do all sorts of different ways of doing it, but ideally you want single thread performance, but efficiency is the problem. Amdahl becomes a problem. You end up with multi-core in there, and you want to parallelize things. And it's getting the right type of parallelism that's the challenge there. And you need to know that your algorithms are going to run on the hardware that you're building. Now, when we started doing Imperas some 10, 15 years ago, we were working on helping people with parallel hardware and building platforms to help them. There weren't any really good applications out there for them to choose. So a lot of people built parallel hardware, but actually there weren't the software suites for them to really optimize. And most of them fell by the wayside. Their silicon worked, but they couldn't find the application space for it. If we switch forward to now, what we have is, especially in the machine learning, the AI space, we have all of these different software solutions out there and certain frameworks that people want to use. And the challenge is there's a tremendous amount of computation needed. And we need to increase that the performance of the hardware. But the great thing is these frameworks exist, so there is something to target with the hardware. So the software is sort of beginning to be sort of stable about what applications you want to run. So now it's a matter of choosing the hardware parallelism and architectures that really can help that. So that's a good thing from a processing in parallel point of view. There are the references to run on, and there's many different architectures out there that people are going down. On the left here, you could have multi-core, and they could be very large cores. Moving to the right, you might have an array of many smaller cores, and each one of these cores actually could be a single CPU shown up in the top right in green, or it could be a cluster of maybe two, or maybe it could be a heterogeneous cluster where you've even got custom instructions in there. So there's many different architectures being done, and our customers are actually doing all sorts of different architectures with our technologies, from simple multi-clustered to those with extensions, with those in heterogeneous things. And the great thing is that you don't just have code snippets to test these things on, you have the full application workloads to be trying. And as I said, we've got customers sort of that are using our technology, and they use us for architectural exploration, and they use this to help with their partitioning. But one of the key things that they're trying to do with using simulation is move their projects to start earlier, and what they call it shift left of the project schedule, so they can actually start software development before the actual hardware is developed and available to them. And also that if you've got platform partners that want to use your chips that you're building, you can provide them simulation models early on so that they can also start shifting left and working well before the silicon's available. So it means when the silicon's available, it means you've got the customers and people with their software already up and running on it. And so people are trying to do these different architectural explorations. And one of the things that we've got customers starting to do with other ISAs and now with ARM is starting to look at custom instructions, where you can, with ARM, with the ACI and the data path extensions, custom instructions, you can tune single thread performance and optimize that. And that's really what we're going to be talking about going forward. So now we're going to talk about here a little bit about how you you can tune your hardware using instruction extensions. So before I do that, let me just give you a little bit more information about Imperas. So as I said, we build these virtual platforms. We have a library of processor models of over 250, of which about 60 of those are ARM cores from the early ARM 7 stuff all to the multi-core SMP multi-cluster things with big. LITTLE now. So we have a very large component library of processors, but also we have behavioral components as well. So we have the USBs, the Ethernet, CAN, things like that you can put on your device, and a lot of them actually sort of virtualize so that if you have an Ethernet device in your simulation, you actually can send packets on your PC's Ethernet, or if you've got a USB peripheral being simulated, you can plug in a USB stick in it and actually and use that, or a USB hard drive or something. So we've got a large component which allows you to bring that together and build platforms, and it's all based around something called Open Virtual Platforms, which is an open standard way of modeling. And that's all of the models that we develop are actually open source using that standard. You still need a simulator and tools to run those models. And that's what we provide commercially as our simulators in there. And we can simulate from the small, simple core, simple behavioral components all the way up to the full SMP systems. And we have very high performance in the billions of instructions a second on a regular sort of PC laptop. We can model from single core, multi-core, multi-cluster, asymmetric, symmetric cores, heterogeneous, homogeneous. We can pretty much model anything that you've got in there, multi-cluster. You can even communicate with Ethernet across them and everything. So we can go from bare metal all the way up to SMP Linux and boot, an SMP Linux in something like 10 seconds on a laptop. Our simulators are all instruction accurate. They're targeting the software to run. So the software cannot tell that it's not running on the hardware. But we do have the ability to do timing annotation. So if you want to do sort of cycle approximate performance analysis, you can actually add timing information to some of the simple cores that are available. Now, as I said, we've been working actually for quite a while with people extending and building their own instruction sets actually, and taking established instruction sets and extending those. So it's very exciting, I think, when ARM about a year ago announced its ACI custom instructions and its custom data path extensions. And I really think it's a brilliant way that it's done, in that it is predefining what the decode should be and just allowing you to extend the blocks underneath it. Because in other architecture where people allow you to extend, you can put any instruction decodes you like and you can overlap the existing ones and you get terrible fragmentation and mess. But the ARM approach is saying, okay, here's your 9 or 12 or 16, whatever it is, decodes, and say, this is the format of the instruction. You just have to add the behavior to it. I think it's a brilliant approach. And we have a modeling approach that works really well with that, in that you have the base model that we run and we test and we verify and everything. But we allow you to add extension instructions and state, actually, if you want, on the side as an extension library to it, without disturbing or touching the actual the model that we have spent a lot of time building. You could, we provide the source, but actually it's a much better methodology to add it to the side, so then you can keep up to date with updates and things like that. So we have the ability to add the instructions, the ability to add the custom data path extensions and the functionality of that. So it allows you to model and simulate and run those. And our technology works with that. So from the instruction levels, assembly, trace, and disassembly, all the way through to the debug. And we can analyze the effectiveness of these instructions by adding timing estimation data in them. And you can create these models for yourself of these components and add them, or you can share them with other people. So that's what I'm going to talk a little bit about that. And so there are many different things, and we have to do analysis to try and find out how things can be improved and the performance increased. So we have a methodology, and here on this slide, I think there's five different sort of phases in here. I'm really in this presentation going to talk about the first three, really, to add new instructions. And in the top left, the first one is the first thing you're going to do is characterize your application. So you get it running, you compile it up, you run the ELF or whatever, you run instruction accurate simulation, use the trace, debug, analysis, get it going. And then you make sure you've got the timing simulation in there, and then you do profiling with it. When you've done the profiling, you can then see where the areas that need improving are, and you can then start to think, okay, I want to add some new instructions in there, so you need to design them and everything. And I'm going to talk a little bit more each one of these flows. And then when you've done that, you've added timing, because you can estimate the timing for those, you then can do the profiling again, and do analysis again, and then iterate. So you do some measurement, you do some changes, you remeasure it, you go around that loop. And we have all the technologies to do all this. And when you're happy, you drop to the bottom right box where you can focus a bit more on optimizing the model for other users, check the coverage to check for testing and stuff. And then you can actually deliver those models to your different users of there. So the example that we've been using is actually from a security algorithm, Cipher security algorithm, Tetrad 20, and the algorithm makes heavy use of things like XOR and rotation instructions, which are called quarter rounds. And as people are moving complex things from the cloud to the edge, they're going to need much more need for things like these protocols. And the custom instructions really help, because they help from two things. One is, if you were to just do this in sort of standard instructions, it would often be very easy for someone to watch what is happening. Put them into custom instructions, and actually it's not very easy for people to see what's going on with them. So first thing we would do in the software-driven flow here is you do the characterization of the existing thing. And an example of that here is we would look, and so if we look here at the top right, we can see there's a function called process line, which does these quarter rounds in there, and then that's called in a loop here. And we would run, we'd have to compile it up, we'd run it instruction accurate. We have the ability to do what's called semi-hosting. And if you look somewhere on the right, top few lines up from the bottom, you see printfs and close and things like that, rewind. We have this what we call semi-hosting, so that you could just take that program and run it on your simulation. You don't have to bring in extra libraries or write sort of drivers and things like that. And so you get your algorithm running at that sort of level, and it runs very fast, billions of instructions a second. We then go to the middle and start doing a bit more analysis on it and do some profiling. And the profiling, here's an example of this with the timing in it. And the original profile, top right, you can see that actually the second box there is process line in there. And so that's using instruction accuracy simulation with timing analysis in it. You get that. What you then do is add your custom instructions in there, and you'd see that actually that it has changed. This is not showing how fast that with the custom instructions or without it. It's showing that the relative performance and where it is spending its time, its profiling. So it's relative performance. And you can see here that process line has now dropped down to some 14% or something of the whole thing, whereas before it was actually not just the top yellow thing, it was all the green bits as well, because there were some functions of it. And so that you can see that when you simulate, you get the profile data out in there, and you can see this estimated improvement in throughput of your application. And that's the key thing, is to show how much better it is with the new instructions in there. So having said that, and shown that, what can you do with these models? Well, we have our framework. It's all an Eclipse-based environment that runs the simulation underneath it. And one of the key things is, just by adding these new instructions, all of our tooling just understands it from the get-go. Now, ARM has been very good, as I said, and just said, okay, so these are the decodes. So it actually simplifies it a lot. But some of the other instruction sets we deal with, they let every designer do what they like. And so our tools have been built up to understand what people are modeling and do that. With ARM, it's a lot simpler. So anyway, so the tools will the debugger and the analysis tools and the tracing and everything understands these custom instructions. You can simulate and run it when you add this. There's nothing extra that's needed in any of the tools there. And just to drill down a little bit in what's available in the Imperas environment. So in the central box on the left, you can see the sort of the virtual platform. You see OVP CPU, and that's really the processor model. And around that, you can model buses, you've got memory, you've got peripherals in there. And that's in the sort of what we call a virtual platform. That then can actually talk to a test bench that actually can be C, C++, System C, or Verilog. On top of that runs an application, software running on it, but it's driven by a simulator. And our simulator is a just-in-time code translating simulator, an extremely fast modern technology. And we have this technology called Slipstreamer around it, which is a bunch of APIs, which allows us to introspect and get callbacks on everything that's happening in the simulation. And from that, we can layer on tracing tools, coverage tools, profiling tools, analysis tools. We can extract waveforms if we like. And then we have a full debug analysis environment around the Eclipse environment. We can not just look at the sort of the pins or the variables in there. We can also abstract, and with our technology, look at the functions that are going on, and that's part of how we do the profiling. We can understand where a function is, and we can trace tasks and operating systems in the schedulers. We can also actually do fault injection if we want to analyze how things are working. So we have a whole bunch of tools focusing on the software teams. But again, and if there's custom instructions in there, all of that will just work out of the box. And one of the key things about virtual platforms is that you can use them as part of your continuous integration, continuous test environment. One of the big challenges, if you were to use prototypes, FPGAs, or wait for silicon, is getting the access to those resources if you're doing your testing. And one of the great things about simulation and virtual platforms is that every time you change things, you can do complete verification of them in a continuous environment. So if you had a design, you've added your instructions, every time you check it in, you can do a complete full analysis of it with the simulation of it through that. So you can go through continuous integration, continuous test, and to deploy it as well. And we have many of our customers use a methodology with our technology like that, with custom instructions actually in there. And so one of the things we're very focused on is the way that customers are doing things. And that's what we're trying to do, is to help ARM users with their custom instructions and to deploy those in there. And one of the things we have is not just the individual components. We have a whole bunch of what we call extendable platform kits, which are sort of pre-configured libraries of components for doing specific things. And we have models of standard boards that people have in there. And this is an example here of a project we worked on as a European project with SafePower, where they did a lot of stuff around the using ARM and based around a Xilinx platform in terms of the prototyping, but they used us for simulation on there. And actually, there's a paper at this conference on this work that's been very successfully done as part of this European project that we were a member of across about 10 different places across Europe in there. So we have a library of components that you can put these platforms together in. And I mentioned earlier we had the peripheral models. We have that library in there of the peripherals, and then as I said before, we have the ARM whole library, including the M33 with the ability to extend it with the ARM custom instructions and to add the custom data path extensions in there as well. And then once you've built that component, you can then have 4 of them on a platform, or 64 of them, or whatever you want in there. And each one actually could have different instructions if you different implementations, if you wanted to do things, or maybe try things out in different ways. So we have a capability to allow you to extend the processor with these instructions and then simulate and validate it and verify it with them. So to wrap up really there, we believe that these ACIs and the data path extensions by ARM, adding these in here is a brilliant thing to allow people to customize an existing process and tune it in specific areas to make single threaded programs run a lot faster. And so we think it's a great approach to allow people to give them that flexibility, that freedom to extend things. And Imperas, our focus is the tools which help you do that and to be more efficient and to help you tune those and get the right ones in there. So, we're a simulator company with tools around it. We do a very fast simulation in there, and you can use it well before RTL in there. It can be full platforms with full OS support, SMP, Linux, and everything. We have all this analysis technology as well to allow you to try out new hardware concepts, new instructions that you're trying in different configurations, because we have all this software analysis tools and the debug tools and the libraries to do it. So you can use this for architectural exploration, software development, and extending with processes. So with that, thank you very much. And I believe there's going to be a Q&A session now following on from this presentation. So thanks very much.